Alright, so for this year's internship, we had 3 separate projects that we extended from last year's internship. One of them was the isolation and purification of ADH utilizing salting out methods that we kind of have named, and aqueous polyphase solutions. We also attempted to isolate caffeine using the aqueous two-phase method that they discovered last year, and we investigated ADH active site. How do you explain that?
Sterics.
Sterics? All right. Right here is a close-up of baker's yeast. It's used for baking like bread. This is where we derive our ADH from.
What is ADH?
It is the abbreviation of alcohol dehydrogenase. It is responsible for the oxidation of alcohol, as seen in this reaction right here. So ethanol, which is an alcohol, accompanied by ADH and NAD+, which is our cofactor in our reaction. Ethanol, because of ADH, is then oxidized to acetaldehyde, and then NAD+ is reduced to NADH, which we can witness at, observe at 340 nanometers. So alcohol dehydrogenase was first purified and crystallized in 1937. The point of our research is to try to find an alternative method to do this, to save time and money. So Racker was in 1949 wrote the assay, which is the experiment that we use today to determine the concentration of alcohol dehydrogenase in a solution. So from Racker's assay is where we have a Racker unit, which is a unit of concentration that when we observe a change in optical density of 0.001 per minute. In our experiment, we use a spectrophotometer to witness the absorption of NADH, and this is an indirect measurement of the activity of ADH. In our Racker unit, the higher our Racker units are, we can then conclude the higher the activity of ADH in our solution. So here's a picture of an aqueous two-phase. That's when you have two solutions that dissolve in water, but when added together become immiscible, which you can see by this interface right here. They want to separate. So in our research, we're hoping that with diffusion, we want to separate and isolate the ADH into one of the layers.
Thank you. So last year, when the research was done, they found that PEG as a polymer worked very well with ammonium sulfate as a salt. When they mix, they always form an interface. So since we're purifying since we're purifying ADH with this ATP phase system, why not try a different molecule, right? So we wanted to try caffeine. What I did was I extracted, or was trying to extract, caffeine from Lipton tea. It did form a polyphase, but it wasn't as viable as I thought for research. Nothing is ever what it seems. Right here is just a picture of ammonium sulfate, the tea extract that I was trying to purify caffeine from, and a PEG layer. The polymer, the PEG, or the ammonium sulfate, or the salt is what they found worked best for purifying ADH blasting. So I put them all in a separatory funnel. I kind of shook it gently, and it wasn't viable. This is all PEG, and that's all the caffeine and a bunch of other gunk. Really not ideal for purifying. These are just some pictures of test tubes when I mixed the same mixtures of caffeine, PEG, and ammonium sulfate. This is test tubes before the centrifuge, because I put this in a centrifuge. I mixed up the solution, and this is what popped out of the centrifuge. Again, a lot of other gunk. This is not a viable method for purifying caffeine. So how did I test if there's caffeine or not inside the test tubes, inside the solutions I was trying to extract the caffeine from? Well, I used a UV vis. The method I use, since caffeine absorbs light at 280 nanometers, I popped in a sample from each solution into this UV vis, and from that I'd get a reading on a graph where there'd be light reading at 0, and there'd just be a spike at 280, and that's how I determined if there's caffeine or not in each solution. And for a baseline on the weight of each substance, I used the dichloromethane procedure to extract pure weight of caffeine. And once I did that, I just let it go off. I tried extracting pure caffeine from 5-hour energy drinks, Starbucks coffee, chai tea latte, and AM PM dark roast. And this is all pure weight of pure caffeine in each. Pure caffeine per 50 mils or per Lipton tea bag.
And that's a method that's just been used a lot.
Yes,
before,
ma'am.
right?
I use that method as a baseline.
Yeah, we tried to incorporate the successful method from last year, which we used to purify the ADH. We said, hey, maybe this is viable for separating other compounds and that will eliminate the need for toxic organic solvents that we had to use, and we were going to actually put in that.
Right.
But it didn't work.
Jensen, real quick, on your
It's in both
on your
phases.
absorption measurements with your tea, did you do backgrounds on the other compounds to make sure that you weren't getting readings from something interfering?
Yes, ma'am. And from that data and from the data I got from my samples, that's how I knew how to roll out that.
Okay, so
There's
you
nothing here.
checked all of the
Yes,
like
ma'am.
raw tea and bags and stuff?
Yes, ma'am.
Okay.
Yes, ma'am.
Well, now going back to the aqueous two-phase layer, what we did here is try to duplicate what happened last year, the experiment from last year. So what we did here, we got more polymers, and we try to attempt to do an aqueous two-phase layer with those polymers. So what happened here is that it was something that amazed us when we used the polymers and attempted to do the aqueous two-phase layers. Because in this case, we were trying to use, we used the same salt, which was ammonium sulfate, and we used a different polymer. Instead of using the PEG, we used the hydroxypropylmethyl cellulose, which once we added those solutions into a test tube, it did form that aqueous two-phase layer. However, what we did to check if it was actually an aqueous two-phase layer, we mixed it to assure that it was causing that aqueous phase layer. However, what happened there is that white interface that forms between the aqueous two-phase layer, the aqueous on the top and the aqueous on the bottom solution, was actually a precipitate. So what we did is we mixed it, and we found out that the interface, the white interface that was forming, was actually precipitating out the polymers of our polymer solution. Yeah, so what we did, this is a picture of what happened. This right here is the salt solution added with the polymer solution. And this right here, this is the white interface that's causing to partition those two-phase layers. Now what happened is that after mixing, everything was just a one aqueous solution, and we were causing the polymer to precipitate in a glycol. So what we did, knowing that, knowing that process, we took that into account, and we added that directly to our ADH solution to precipitate our ADH, our enzyme.
Okay, so salting out. There's two aspects of salting out. There's the salting in and the salting out. When you have a protein in a solution and you add a small amount of salt to that solution, the protein is still soluble. But as this graph right here indicates, as you keep adding salt into the solution, you'll reach a critical point. And this critical point, after it gets past this critical point, the actual protein becomes insoluble, and this allows for the protein to be precipitated out of the solution, which we did pretty good here. And okay, so salting out, we used a different variety of salts to salt out the ADH. from literature values and references that we found, the ammonium sulfate was the best one, but we went ahead and tried different salts to see if we can get the same results. So we knew that the ADH had to stay in an appropriate pH range from 7.6 to 7.8. So we went ahead and fluctuated the pH to get, for those salts to get to that point. And we went ahead and put those salts with the ADH inside a test tube and allowed it to precipitate overnight. Some of them did, while others didn't. And the potassium iodide seemed to be the one that produced the most precipitant, but we went ahead and ran the assay on it to check for Racker units, and it wasn't really viable, which meant that it didn't have too much activity. So we kind of just scratched that out and went ahead and went with the saturated ammonium sulfate as the best salt, because after running centrifuging and allowing it to precipitate, that one gave us the best protein at the bottom. And here's the stock solution with the ADH, and the tris was the solution that we put the ADH into. And as we went ahead and centrifuged it for an amount of time, we had to pour off which with the supernatant, because the precipitant would get, you know, a small pellet on the bottom of the test tube. And as we centrifuged it, we ended up having this protein right here, which we went ahead and added some more solution to preserve it for a longer amount of time. And as we assayed that protein, it indicated that the ADH was there.
So, when we were messing with the other salt solutions, we found out that there was something that we weren't getting consistent results. Sometimes we would add it and it would precipitate, sometimes it wouldn't. So we went back and we did some more research, and we figured out a different procedure to try it. And so we started, instead of adding the stock ADH to our salt solution, we add the salt solution to the stock ADH. So that way it would start off diluted, and then we would build the concentration of salt in that solution and salt out the proteins. We did this in different amounts of volume at a time. At first we tried 1 milliliter at a time, and then we would salt the protein out and centrifuge it, and then we would dissolve the protein, pour out the supernatant, dissolve the protein, and run assays on it. And we did this 1 milliliter at a time, 2 milliliter at a time, and then the final 3 milliliters. And we ran assays to figure out which one worked the best. And not really to any surprise, it was the 1 milliliter at a time. It gave us the best precipitation of the protein.
So my part of the experiment research here at McLeod College was dealing with polymers of different types to create polyphases. And at the beginning, we all started with 11 polymers, all these different polymers, and we had to kind of derive our own ATPs, which stands for aqueous two-phase systems, with these polymers. So after doing all this mixing and finding out which ones made ATPs, we tested the Rack units on a lot of these. And also this is all with water as a solvent for all these polymers. So once we went ahead and found out which ones create ATPs, we then graduated it out to form polyphases. And this is our next matrix here with tris as a solvent. And the reason why we use tris as a solvent is because a lot of times in the previous slide,
So what Daniel's doing is, instead of having 2 phases, he's going to try and create more than 2 phases. 3, 4, 5, 6 phases. 4 or 5 aqueous phases, all separated out into layers. That's like,
That's
We did it.
crazy.
it's so contradictory.
You did it?
we got proof.
Oh,
Yeah.
We
show
did it.
me.
So, and before I show you which ones we graduated, we wanted to make sure that their rack units were really high. So the reason why we had so much tris is because some of the rack units were 0 with water, whereas with a DA dextran, it increased with tris. So that's why we use tris as a solvent as opposed to water in some of them. So for example, hydroxypropylcellulose had 414 rack units, as opposed to with tris 1,104 ractants. Great
Is
increase.
tris a polar? Tris is
It's
a
a
solution?
buffer, it's a buffer.
Oh, okay. Yeah, that's right. Okay.
And it's obviously stabilizing, maintaining the ADH structural features that are keeping it active.
But you measured the pH of your water too. It was at the right pH. It's
Yeah.
Just, okay.
Yes, these are actually the pHs right here. Actually, multiple polymers. And so, as you can see, they're not super alkaline and super acidic, which is kind of near final range. And so that's why they all graduated, because they all did fantastic as far as racketies were concerned. So we ended up using PEG, HPC, polyvinyl pyrrolidone, and acrylic. So these are all our 4. Now this is an example. Here's our 3-phase. 1, 2, 3. After we found out which ones made ATPs, we then kind of determined which polymer went where in the polyphase. So we determined the position of each polymer in each polyphase. So these are just examples. This is a 3-phase. You see it's a very clear interface. It's hard to see as far as the other salted ones. There's another interface right here. And this is a 4-phase. This is 1, 2, 3, and 4 with a slight interface right here. So that's just an example of our polyphases. And here's actually a video that we have.
Okay.
And this is actually the 6-phase. 1, 2, 3, 4, 5, 6. And we're gonna actually just show you a cool video of us how we mix it. And as you see, they kind of go back to their spot. And this kind of determined the strength too. A lot of times, we actually had a pseudo-phase here with the dextrans, so we ended up throwing out 2, and that's why we ended up with a 4-phase at the end. But after mixing.
So were these kind of like gels, like PEG is? They
PEGs,
connect-
yeah.
And
PEG
there's
was
different densities.
Cellulose was a little jelly. Yeah,
Mhm.
they all have different densities as far as that. Yeah. So that was an example. And then so the 4 that did graduate was HPC, PEG, polyvinyl pyrrolidone, and acrylic. And so what we did, we went ahead and put in a polyphase, and then we assayed each of them. But this particular method was used when we sandwiched a 0.1 ml of ADH in between each of these polymers. So when we did that, after we kind of looked at it, we see that there was unfair treatment here. As you see, PEG and PVP both had a greater chance of receiving the ADH as opposed to HPC and acrylic. So then we recreated it with each one having a fair treatment of ADH right in the middle, and it just so happens that PEG and PEG and PVP both had higher raffiness as shown in this one. So that was a good result.
Coincidental.
Yeah. And then we actually had a better method. Instead of sandwiching it, so we don't have to do that whole different thing, we ended up using it as a solvent. So we actually put that 0.1 ml into each of these solvents, and again assayed it, and PEG again and vinyl both had good high rack units. So the ADH was diffused into these 2 middle polymers. Then after we did that, now that was all with pure ADH, by the way. So that was all with a pure ADH. And the point of this research is to purify stock ADH. So we then did it with stock, and we have our rack units here. Our baseline for stock was 1,064, and after we put it in the polyphase, they went up. So we could say ADH was isolated into these middle polymers here.
Can you explain what is stock?
Stock ADH is just our original grounded up ADH that we got from the brewer's yeast.
Baker's
yeast.
Baker's yeast, yeah. So that's just our stock sample.
Oh.
And then so we hope that all the impurities were at least.
So they added ADH to each one of those polymers. So each one of them started out at 1064. And you see the HPC lost the ADH into the PEG, and the acrylic lost it into the vinyl, which were adjacent. It was compromised before because they were layering. And so PEG, for example, would have
You have to
2
travel through
layers of
something else to
ADH,
get
so
to.
it's got two sources for it to get to, whereas the HPC was only had the layer of ADH underneath. So they had to modify that a little bit. But the results are consistent.
Yeah.
They were consistent. And it indicates clearly that the PEG and the vinyl will partition the ADH more readily than the larger polymers. And one of those polymers is actually a salt, which had an effect, which you'll explain.
Results. Yeah. And then so pretty much, yeah, so after we figured out that the ADH liked these 2 polymers most, we then wanted to mix it with the salt to see if we can isolate it even further. So when we did that, again, we used the same 0.1 ml of ADH as a solvent, but this time we used a desalted out stock solution. So we didn't use our original stock, We used it after the salt group added their salt to kind of purify it further. So their baseline, which was a 111 dilution, was 116. And so it just so happens that PEG was the only one that increased the rack units. They actually doubled, pretty close. And acrylic, as being stated, was a salt, ended up having no rack units. But definitely the ADH was all diffused and isolated to this PEG layer. So it was a great result for us. And this is just a graph showing that acrylic did terrible with it. And this blue here is represented by PEG, which increased as it went. And these are just, there are two polymers where they didn't do so well in that last part.
Yeah, do you have a theory, Daniel, why the
Uh,
acrylic went to 0?
Okay, so it reached threshold. It was the salt concentration. It reached this threshold, and that's pretty much it. And the nature of the protein.
Yeah,
So
so that would be a good guess.
So that would be our
So
guess.
the salt basics, and that's why it precipitates out too, right? When the salt concentration is high enough, the protein changes shape, changes composition, and it changes the external structure of the protein, right? So
Mhm.
now it's no longer soluble in the water.
Well, the acrylic is actually the only polymer up there that we purchased as the sodium salt. So because they used the salted out purified protein from the other group, there was probably a really good chance that there was some residual salt left in that solid.
Mhm.
And when you dissolve that into the polyacrylic, which was also a salt, the only explanation is that you pass that salt threshold and denature the protein. Because we did run the polyacrylic with the non-salted out ADH, but the ADH that came directly from the baker's yeast, and it showed activity. So that graph where you can have the solubility of salting in and salting out, that extra salt that was added by the polyacrylic in its solid form just must have pushed it over its
And
edge.
how could you test whether there was salt in there?
Yeah, we can't. We couldn't prove that. We're going to probably deal with that next
Yeah, salt bridge.
next
To be
week. Yeah, next year. Yeah, that's one of the. We salt out the protein and we see it spun down there in the pellet and we reconstitute it into the tris, and there still could be some salt there, from the residual salting out.
Good afternoon, everyone. As a side project, I was tasked to play around with sterics, or investigate the active site of the enzyme alcohol dehydrogenase. So at first, we wanted to figure out if big and then small molecule interactions would matter. So I added NAD plus cofactor first, the pure ADH enzyme second, and then the ethanol, which is a smaller molecule among the three, last. When compared to the baseline assay run, there was no significant change in activity. So we figured out, all right, since big and big, small doesn't matter, why not big, small, and then big? So we went there, added NAD cofactor first, small ethanol second, and then the ADH enzyme last. And then we figured out that there was no significant change in the baseline assay run. So we went a little step further. Since we're dealing with polymers, why not mix the enzyme with the polymer, correct? So before running the assay, order variations, pure ADH was mixed with the 4 polymers, the 4 best polymers that were used for the aqueous polyphase layer. And then we found out that there was no significant change from the baseline assay runs when compared to. So we concluded that the order of the component addition between cofactor, enzyme, and substrate has no significant effect on enzyme activity, even if the enzyme was mixed with polymers. So, and then we were not done with that. So we decided to play around with alcohols. Pretty sure everyone's familiar with that. So we wanted to play around with straight chain versus compact polymers. So based off the graph, N-pentanol was insoluble, so it was inconclusive. We played around with N-butanol, which gave out 352 Racker units. Compact alcohols, secondary butanol and tertiary butanol, both were pretty low or inconclusive in terms of activity. And then isopropanol showed some activity, but then at the end, ethanol and N-propanol showed high levels of activity. So from that, we could say that the active site of the enzyme supports straight chain molecules as opposed to bulky and compact ones in terms of steric hindrance and electron repulsions. So in conclusion, sorry.
But glycerin.
Oh yes, glycerin, Professor Kennedy just wanted me to play around with it. It's basically considered a straight chain, but it has 3 hydroxyl groups on it. So it showed some promise, little activity, but ultimately ethanol wins among all the other alcohols that we played around.
Dante, N-propanol is pretty close second place there.
Yeah, and propanol is a pretty close second place. So we could think about it this way. It could still function just like ethanol, but since there's an extra carbon chain in it, it could just be sticking out right out of the enzyme substrate complexes in the active site. It's straight chain propanol.
Because N-propanol looks just like ethanol, except
Except
for
one
the,
longer carbon.
so
Yeah, just an extra
approaching
carbon.
an enzyme in the proper orientation, the enzyme might not be able to distinguish.
Can we back up for a second? I'm not
Sure.
sure I totally understand the role of the enzyme.
Which one?
Which one?
The enzyme oxidizes.
No, like which slide?
No, I don't mean to back up on the slide. I just
Oh, okay, I'm sorry.
Just sort of the enzyme oxidize. What does the enzyme do, and what is the point of having ethanol in it?
The enzyme oxidizes the ethanol. It's the way the body processes that
Okay.
toxic content. It
Okay.
actually turns it into something more toxic, right? Acetyl
Acetyl, okay.
And so when you're
which is
looking at
process.
the RU, that's Rucker?
Racker
Racker
units.
units.
Racker units?
Yeah.
I thought you were measuring the concentration of the activity of the ADH.
We are. The Racker units measures the concentration of the enzyme, right, which is directly related to activity. It's just another application. You have to apply Beer's law to it. So we do the concentration in Racker units, and then you do Beer's law, change in absorbance is proportional to change in concentration. Here, one of the downsides to this particular assay is that you're trying to determine or measuring or characterizing the activity of ADH not by the disappearance or use of ADH or the formation or disappearance of ethanol. You're using some third molecule to do it. And of course that opens up a debate on, is there anything else in there that can reduce NAD to NADH? Is that the only source?
So you're measuring the enzyme, and right now this is a test of how.
Different substrates.
So, okay, and so therefore the way you're basically binding the active site with the.
That's right, and it was surprising because the old theory of enzyme substrate complexes was lock and key, one enzyme, one substrate. Now we know that's not true. That's given way to the induced fit theory. So.
Induced fit theory?
Yeah.
Okay.
Yeah, that was developed by a guy named Daniel Koshin. He won the Nobel Prize for that, I believe. And it says that, there's pre-binding interactions between the enzyme and the substrate that allow the coupling of and formation, therefore, of the enzyme substrate complex. And again, when enzymes are catalysts, so they're not used up in the course of the reaction. They're not changed by definition. So the substrate changes, it's spit out of the product, and the enzyme goes back and gets more substrate, and it's kind of recycled. And these were somewhat surprising results that the enzyme, this is clearly evidence that the enzyme is not a lock and key. It's not capable of differentiating exactly between them, because the propanol is a 3-carbon chain. Can you draw it up there, Dante?
Sure.
A 3-carbon chain, and compare that to the structure of ethanol. There's ethanol, now there's propanol, now do one more with the OH. It's okay. OH. Now you can see how similar they would be if the approach of both of those molecules to the enzyme, say the slide or the lighted area is the enzyme, if they're approaching that same way, to the enzyme at least, they would appear the same through the first 2 carbons. And then if that's all they can differentiate the enzyme is the first 2 carbons, then the third one can just be hanging out there. And that's further evidenced by N-butanol, although with
Being your
Third highest.
yeah, but the N-butanol, you're running into more of the, they have all of the
twisting.
free rotation around the bonds.
The sp3.
You can have the gouge and the eclipse forms, and so it's not terribly surprising to me that it's not as high as the other ones. But I was really surprised by the N-propanol result. I thought that it would have the ability to distinguish between those two primary alcohols. But so we should run all these experiments with N-propanol.
Alright.
Sorry.
Yeah, that's fun. That's pretty cool. So, in conclusion, the enzyme active site readily accepts straight chain alcohols, ethanol, N-butanol, and propanol, with having ethanol and N-propanol as the two best substrates. And then due to steric hindrances in the enzyme, bulky and more compact substrates, isopropanol, secondary butanol, and tertiary butanol, were not readily accepted. And then also solubility plays into account when running the entire assay, because going above carbon 4 makes the solution in the assay immiscible, and which caused a change in absorbance already before even adding the NAD cofactor, which would make all results inconclusive. And so, on behalf of the entire Winternship team, I would like to thank NSF Chris, and special thanks to the Cal State San Bernardino for all their support and letting us having this really grand research experience that we would never have anywhere else. So thank you. Could give them a round of applause. Questions?
Comments or concerns?
One thing that we discovered pretty quick last year, one of the really hallmark things that we discovered last year was this really clean, quick way to isolate the enzyme. Before this, John would take 3, 4, 5 hours using toxic chemicals, lysing, chemical lysing cells, the whole big, long, drawn-out procedure. And last year, we found that we could just literally take the baker's yeast, put it in a mortar and pestle, mechanically pulverize it, crush it up into a powder, add this tris buffer to it, put it in the centrifuge and spin it down at 4 degrees. And it was very, very active. And that was right last couple of days. Well, we began this Winternship with that procedure. And I've actually put that procedure into the 207 enzymology lab. That's how we isolate the enzyme used for that experiment now. And we ran it with the normal tris, and we found that it only lasted about a week, and it died off. That it became inactive by isolating it in that manner. And so someone had the idea to, I don't even know who it was, to saturate the tris, to increase the concentration of the tris for another experiment. And we said, well, wait a minute, what if we use that saturated tris buffer to extract the enzyme from the powder? And we did that, and we found that it lasted much longer. So now that's another thing that's got to be incorporated. In fact, I think from now on, every isolation and everything that we do will be done with the saturated tris buffer.
However, when we created our stock with the saturated tris and we were salting out the protein, it wasn't as pure as when we used the regular tris and salted out the protein. The regular tris stock solution was more white, and then the other one was darker, and then the pellets and the proteins would be a different color. And so we tried making the pellet and then using saturated tris to preserve it, and that worked really well.
And another really surprising result they had was in the salting out, they found more active and more purified enzyme if they salted out, all other conditions identical, salting out from a diluted stock than from the actual stock that they pulled from the baker's yeast. So the example there, they have the stock ADH there in the tris, and what they would do for a typical experiment, they would spin that down at 15,000 RPMs 15 minutes at 0 degrees. And they would extract the supernatant off, and they would add the salt to the supernatant and precipitate the protein out. That's exactly what happened. Then they would spin those down, take the supernatant off, salt it again, take the solid, that was a purified ADH. And they would do that 3 times with 1 ml portions, and they tried once with a 3 ml portion, once with a 1, once with a 2. But it was interesting that when they took the stock solution, they actually diluted it 1 to 3, and they ran the exact same experiment, and they got more ADH, and it was more active from the diluted stock material. We didn't have time to go into that, but I told them this thing is going to branch off and take on a life of its own.
Yeah.
And this is one of the really intriguing things, because that goes against all really kind of logic. You shouldn't be able to salt out more active and better quality protein
more
from a
dense.
dilute solution than a stock solution, which should have more of the ADH.
And you
So-
can, it was very clear too, because when we used the pure ADH and we salted it out, it was like opaque. It looked like there was a lot of colloids in it. I don't know, it just wasn't as good. So we did the 1 and 3, and then we added the salt, and the proteins would literally form. We would add the salt dropwise, so you could see like the salt hit the surface of the water and split up, and you would see proteins forming as it did that. So
You mean an aggregation of the proteins like this?
Yeah.
Yeah, the aggregation, so the protein would be suspended in the solution, and then we centrifuge
and it would grow.
add the salt solution again, and then centrifuge and take the precipitant out. We even went through the process of adding solid salt in there to see if we can maybe precipitate it at a faster rate, but
Does the precipitation, does the G-force on that do anything to the conformation of the protein?
No, just temperature. That's why we have to. That's why we have to run it in a refrigerated centrifuge,
Yeah.
because the sheer friction of spinning at 19,000 times G or 15,000 RPMs, it heats it up, and that'll kill the enzyme. So we had to buy the $4,000 refrigerated centrifuge. That's why we did it, because it's more expensive to isolate or to. It's like literally, what is it, John? It's like $150 for
50 milligrams.
50 milligrams of purified ADH.
Yes.
So we gotta buy the
Centrifuge.
centrifuge and make our own from Baker's. You get a big old thing of Baker's used for 59 cents. You know? Yeah. So it was, but we ran that in the past, and just the temperature change of it, running those speeds killed it.
One of the most interesting things that we found was that every day when we came back and these guys would make their stock ADH, it would turn brown again. And more brown as more and more thick.
Yeah,
So
that was-
they were like, damn, what are we gonna do? And so one of the things was that they had to centrifuge their stock ADH at least 3 times
yeah, 3 times.
in order for all of the actual yeast that kept reproducing every day. And we were like, well, what is going on with that?
Yeah,
And
that's intriguing.
that was one of the things that we determined was that the NAD was being reduced to NADH most likely through its normal processes, because the yeast was still alive and reproducing itself. So just the normal citric acid cycles, there's 3 or 4 enzymes that reduce NAD to NADH on its own. So we had to ensure that we had no yeast every single day, so that took a lot of time.
I mean, you can get yeast just from the air, so
Yeah,
that's
and
challenging.
we never saw that with the chemical lysis, the other method. So obviously there are limitations to trying to pulverize and mechanically lyse in a mortar and pestle, completely
Is there a
every
way
single.
to kill the
bacon.
yeast without? Chemical?
Now, probably not without damaging the components in there, one of which is our target molecules. It's not that big a deal to spin it down, though, given really the time and cost of that method versus the old method. There's still a whole lot that could go wrong before you would abandon this mechanical crushing, because it's such a finicky enzyme to begin with. It literally, if you have your sample right there, say that yellow stock ADH, if you take your pipette and you put that at the top, the middle, the bottom, and you run assays, you're going to get different activity all the way through. It's just not, it's ubiquitous, but it's not homogeneous. It's just really strange.
The last thing these guys did actually yesterday, after they were done, was they actually came up with a laboratory procedure using all of these methods that you guys have seen. So hopefully eventually we can actually incorporate this entire project into a class. These guys timed it into a 3 to 4 hour lab period. So students can isolate, purify, aqueous, polyphase, whole bit within 1 to 2 lab periods.
And I think this method
Are you guys
has
willing to sell
a
that
lot
to
of.
me this
Yeah,
Wait,
semester? Ready
what?
for some new labs?
our caffeine extraction didn't work,
I'll handle
but
business.
it didn't work because we didn't have the right salt and the right polymer. We used results from last year's. We made a real educated guess, but still we were basically throwing a dart at a blank, piece of paper. So I think that these aqueous two-phase systems can be used as extraction purification, but there's going to have to be a lot of upfront work to figure out what the best polymer and salts are for different types of molecules. Because what we've found for sure is that there's simply not one that's going to work for everything. That was kind of discouraging, although not entirely surprising.
So
I
guys,
thought it was cool.
what's the advantage of an aqueous extraction over an organic extraction?
Well, like he said, the organic extraction, you're working with a lot of toxic molecules, and so the aqueous, it kind of works a lot better for purification, because especially with the yeast, there's so many other enzymes, and
It's
it's
cheaper.
it's a lot cheaper.
The waste ratio.
It's not cheaper.
The wafer, less toxic.
That's all
Better
the
for the
schools
people
are going to
doing
care
it, it's
about.
better for the environment.
It's green.
No handling
green
waste, water's cheaper than methylene chloride.
For now.
Yeah, yeah.
For now.
Yeah, it's-